as n approaches infinity. Okay, so that's going to give us the limit as n approaches infinity, the absolute value a sub n plus 1, which is n plus 1 squared, times 2 to the n times 2 squared over 3 to the n times 3, divided by a sub n, so we're just going to get that one and flip it, times 3 to the n over n squared. 2 to the n plus 1 is just 2 to the n times 2. Okay. So now we have 2 to the n, 2 to the n. That 2 cancels out, and one of those 2's cancel out there. You have 3 to the n and 3 to the n cancels out. Okay, so that's going to equal the limit of n plus 1 squared times 2 over 3n squared as n approaches infinity. Oh, thank you. Well, everything's plus, so. Usually when it's all positive, there's no way it can be negative. I'll go ahead and, yep. So, what did you say about a squared?
No,
oh, plus a squared. Oh, yeah. All right, so that's going to equal the limit as n approaches infinity. N plus 1 squared, we can just make that 2 times n squared plus 2n plus 1 over 3n squared, which is the limit as n approaches infinity of 2n squared plus 4n plus 2 all over 3n squared. So why did I put 2n to the 4th? I was looking ahead to that 4. There we go. Okay, so if we divide everything by n squared, we don't even really have to do that. So we divide this by n squared, this by n squared, this by n squared, and this by n squared. We end up with 2/3, which in this case is less than 1. Okay, so we know it converges. All right, any questions on that one? All right, let's do one more, then move on to the root test. All right. So let's say if we have, want to determine if the sum from n equals 1 to infinity of n to the nth power over n factorial converge or diverge. All right, so we know that our a sub n is going to equal n to the nth power over n factorial, and a to the n sub 1, a to the sub n plus 1 is equal to n plus 1, oh, got my 1 there, to the n plus 1 power over n plus 1 factorial. Okay, so that means our limit, as n approaches infinity, the absolute value of a sub n plus 1 over a sub n is equal to the limit as n approaches infinity of n plus 1 to the n plus 1 power over n plus 1 factorial divided by a sub n, so we just get that one and flip it, n factorial over n to the nth power. Okay, so we can actually do what we did before. Okay, so we know that n plus 1 to the n plus 1 power, it's just n plus 1 to the nth power times n plus 1. And again, we know that n plus 1 factorial is n plus 1 times n factorial. Okay, let me move this over a little bit. So that's going to equal the limit as n approaches infinity of the absolute value of n plus 1 to the nth power times n plus 1 over n plus 1 factorial is n plus 1 times n factorial. Don't really need that parenthesis there. Times n factorial over n to the nth power. Oh, forgot my other absolute value. Okay, so we know these two are going to cancel each other out. And our n factorials cancel each other out. So that's going to equal the limit as n approaches infinity of the absolute value of n plus 1 to the nth power all over n to the nth power. Okay, so we really don't need the absolute value here because we know it's going to be positive since n is approaching infinity. Okay, so we can take these two exponents and kind of bring them together. So we have the limit as n approaches infinity of n plus 1 over n to the nth power.
Wait, sure, is that outside the limit?
Nope. It's just this to the nth power, so if we had that here. All right. So this, we can actually simplify the limit as n approaches infinity. We can rewrite that as 1 plus 1 over n to the nth power. Which it should look familiar, because this is just e, which is greater than 1. Okay, so we know that this diverges.
How do you know that that is E?
Because that's the formula for e.
Oh, I never knew.
Oh, really?
I never knew it.
See, all that stuff back in Math 1000 comes back.
Yeah, it's been a couple of years.
Was it 1000 or 14? I think 1415.
For pre-calc?
Yeah, pre-K. I think it was 1415. Yeah, 1415.
Math 1000 was algebra 2 in high school.
Yeah, so it was 1415. All right, so we know that by the ratio test, the series diverges. All right, any questions on this one? All right. Oh, anyone's still writing? Okay. Okay, so let's say, for example, determine the convergence or divergence of the sum from n equals 1 to infinity, negative 1 to the nth power, square root of n over n plus 1. Okay, so if we use the ratio test, we know our a sub n is square root of n over n plus 1. And actually, we can go ahead and just use the absolute value, since we're going to get rid of that negative 1 anyway once we do the absolute value of the limit. And our absolute value of a sub n plus 1 is equal to square root of n plus 1 over n, actually n plus 1, which is n plus 2. Okay, so the limit as n approaches infinity of the ratio of a sub n plus 1 over a sub n is actually equal to the limit square root of n plus 1 over n plus 2 divided by that, so we just go ahead and flip it, n plus 1 over n plus 2. Okay. So here what we can do is we can divide both of these by n and divide both of these by square root of n. Nope, divide both of these by n. Square root of n wouldn't work.
Where did the square root of n go from a sub n? On the right side, you got n plus 1 divided by n
Oh,
plus
I
2.
forgot my square root of n. Ah, there we go. Thank you.
But you don't
Nope.
have a plus 1 in there. That's the a sub n in the second term.
A sub n plus 1. Where's the square root of n? Why did I put n plus 1 there?
Okay.
N plus
What
1
the hell
over
did I do?
square root of n.
I looked up on it like what?
Y'all can blame calc and trig for wearing my brain out before I get here.
It's okay.
So you have square root of n plus 1, no, n plus 1 over square root of n. Plus 1, square root of n. There we go.
Yeah.
That looks a lot better.
So we have the limit as n approaches infinity. And if we divide this by, let's say square root of n, we can actually just flip those around. So you have square root of n plus 1 over square root of n. It'll be a little more visually appealing. So now you divide these by n and this by square root of n. That actually should go down 1. Okay, so divide by n and divide by square root of n. Okay, so you get the limit as n approaches infinity. You have square root, actually let me put that on the side so we don't have square root of n plus 1 over square root of n. Remember, that's going to be square root of n plus 1 over n. Okay, so you have square root of n plus 1, make that a little bit bigger, over n, divided by square root of n over square root of n is actually just 1. I might as well write it out, so it won't just disappear. Square root of n over square root of n times n over n plus 1 over n over n over n plus 2 over n. And let me fill that in a little bit more and bring that down just a bit. There we go. Alright, so this is going to give us the limit as n approaches infinity. We can make that 1 square root of 1 plus 1 over n over 1 times 1 plus 1 over n over 1 plus 2 over n. Okay. So as n approaches infinity, that becomes 0, that becomes 0, and that becomes 0. Okay. So in this case, you have, oh, why did I put that equal there? You have the limit square root of 1 over 1, which is 1, times 1, so it's going to equal 1. Okay. So whenever it's equal to 1, it's inconclusive, and you have to use another test. And since you have that negative 1 there, the most logical one to use would be the alternating series test. Okay, so go ahead and block that off. By the alternating series test, remember the first thing we have to do there is find the limit of our a sub n, which is square root of n over n plus 1. As n approaches infinity, okay, which is actually infinity over infinity. So we use L'Hopital's rule. So this ends up being the limit as n approaches infinity. The derivative of square root of n is n to the 1/2, so that would be 1/2 over square root of n, because that would be n to the negative 1/2 over the derivative of n plus 1 is just 1. So it actually just equals the limit of 1 over 2 square root of n as n approaches infinity, which is 0. Okay. So this one passes the first condition. So now our second condition, a sub n plus 1 has to be less than or equal to a sub n. Okay, so that means that our a sub n plus 1, square root of n plus 1 over n plus 2, has to be less than or equal to square root of n over n plus 1. Okay, so here you can kind of throw in some test values and see if it works out. Okay, so for n equal 1, for n greater than or equal to 1, n equal 1, you end up with square root of 2. Actually, let's use one that will come out to be, just use square root of 2. Square root of 2 over 3 less than or equal to square root of 1 over 2. Okay, which is true. We have 1/2 less than square root of 2/3, bigger denominator. This is only slightly off on the numerator, so this one's true. So you plug in n equals, let's make this a good even one, 15. Okay, so you have square root of 16 over 17 is less than or equal to square root of 15 over 16. So you have 4 over 17 less than or equal to square root of 15 over 16, which is actually true. So no matter where you go for n, as it gets bigger and bigger, this will still be true. Okay, so we know that passes that condition, so it converges by the alternating series test. Oops, slide that over a little bit. All right, so any questions on that one? All right. Okay. Now the root test is almost like a carbon copy of the ratio test. It's like minor differences, but the results are really exactly the same. Okay. So 1, the series of A sub n converges absolutely if the limit as n approaches infinity of the nth root of the absolute value of A sub n is less than 1. Two, the series diverges if the limit of the nth root of the absolute value of A sub n as n approaches infinity is greater than 1 or is infinity. Okay. So far it's the exact same as the ratio test. Same results and everything. And it's inconclusive if it equals 1. Not ratio test, root test, duh. Is inconclusive if the limit of the nth root of the absolute value of A sub n as n approaches infinity equals 1. That just means you have to find a new test. All right, so let's say, for example, use the root test to determine if the series from n equals 1 to infinity e to the 2nth power divided by n to the nth power converge or diverge. Okay, so you know with the root test, you have the limit of the nth root of the absolute value of A sub n as n approaches infinity, which equals the limit as n approaches infinity. Remember, e to the 2n power, that's just e squared to the nth power over n to the nth power. Okay. So if you wanted to, you could rewrite it, but you don't have to. We'll just say the limit as n approaches infinity of the nth root of e squared over n to the nth power. Okay. Where in this case, your index and your exponent cancels out. Okay. Which gives you the limit as n approaches infinity of e squared over n. Okay. E squared is just a constant, so a constant divided by n as n gets bigger and bigger and bigger is just going to be 0, which is less than 1. Okay. So we know it converges. By the root test. All right. So any questions on that one? Okay. So you want to use the root test if you have a numerator and denominator that's raised to the nth power, and you want to get rid of them. That's when you want to use the root test. All right. So we'll do one more example. Anyone's still writing? Okay. we're not going to be done in